Now, way back in the day when people were just learning how to harness the power of electricity, the three-phase AC motor was invented by this guy. And with this new motor, they needed a way to turn it on and off. So they created this thing called a knife switch. When an operator grabbed the handle, he would move it from one side to the other, and it would connect the motor to power. But this wasn't particularly safe for the operator, since when the switch was almost closed, there were arcs formed at the contacts which could injure the operator. Ouch! So they said, scratch that, let's just put the switch inside of an enclosure to protect the operator. They put a handle on the outside and now they could turn on and off the motor, and the arcs were contained inside the box. So what's the problem with this? Well, you have to have someone stand there and physically operate the switch. If you've got 40 motors spread around your plant, you better have an operator who has great endurance if they're going to run all over your plant to operate those motors. Clearly, that isn't going to work for a lot of applications. So they invented this thing called a contactor. Inside the contactor, there's a coil of wire wrapped around a piece of metal. Above that piece of metal, there's another piece of metal that is attached to an electrical bridge, which connects contacts on one side to the other side. This top portion, the metal attached to the electrical bridge, is called an armature. When you apply an electric current through this coil of wire, you end up turning the bottom piece of metal into a magnet. The fancy word for this is an electromagnet. When you've turned on the electromagnet, it attracts the top piece of metal, which is part of the armature, and pulls it down, which in turn closes the electrical contacts on both sides. When those contacts close, it allows current to pass through the contactor and down to the motor. Well, okay, that's pretty cool, but how do I turn off the motor? Well, the first thing you do is you kill power to the coil, which will turn off the electromagnet. But that's not enough to separate the electrical contacts. There's a spring inside the contactor. When the electromagnet is turned on, the top piece of metal overpowers and compresses the spring. But when the electromagnet is turned off, the spring is able to push apart the electrical contacts. So what's the point of all this? Well, it allows for remote operation of the contactor, which thus allows remote operation of the motor. If you put something like a push button on the other side of the circuit that is connected to the contactor's coil, then you can turn on the coil from wherever you want. So imagine a control station with 40 push buttons installed on it. And now the operator can stand there and control all the motors around the facility without even taking a step. What I've done here is I've connected a green start button to control power and connected the other side of the push button to the coil inside of one of Eaton's Freedom Series contactors. When I push the start button, you can see the small black rectangle on top of the contactor move up and down. That is the top of the armature showing through, which is moving inside the contactor. You can also hear the contacts inside opening and closing, as well as the hum of electricity flowing through the contactor coil. Next, I'll remove the top off of the contactor so you can see the electrical contacts inside. Watch the armature and contacts move as I energize and de-energize the coast. I've drawn a normally open auxiliary. If you grab a normally open auxiliary off of the shelf, it will not pass electricity through it unless it gets changed by an outside force. When it gets attached to the side of a contactor, there is a mechanical connection between the auxiliary contact and the moving parts inside the contactor. In this close-up view of the contactor, you can see the black plastic clip on the side, which moves up and down with the rest of the armature. This is where the auxiliary contact connects to the inside of the contactor. So, when the contactor pulls down, it causes the auxiliary contact to also pull down, which closes the contact inside of the auxiliary. So what's nifty about this is you can connect a circuit to the auxiliary contact and it will open and close the circuit whenever the contactor turns on or off the motor. Here I've got the same contactor hooked up to a push button. But now let's attach an auxiliary contact to the side. With the aux contact attached, let's wire a red light to it to indicate that the motor is running. Now that there is a red indicator attached to the auxiliary contact, I'll dim the lights and watch what happens when I energize the coil. Basically, the auxiliary contact gives you a status as to whether the contactor is open or closed. Now that we understand how to turn on and off a motor, how do we protect it? Let's briefly talk about short circuits. Well, what can cause a short circuit? When we're talking about motors, one of the ways we can see a short circuit is when we get a phase-to-phase short. So let's say a forklift operator accidentally nicks the wires going to a motor. He doesn't cut all the way through the wire, but enough to cause two of the phases to touch each other. Well, when the wires no longer have the motor in the way, they have an unrestricted path for current to flow. So you end up getting a very large amount of current very quickly through the wire. Well, what's wrapped around wire? Insulation. And you know what insulation doesn't like? Heat. Well, when you put a huge amount of current through the wire, you build up heat very quickly, thus burning up the insulation, and now you've got yourself a fire. Another way you can get a short is if you have a phase to ground short. Let's say that a wire ended up touching the rail on a garage door, and now you've got a path to ground. It's the same problem. One of the popular ways to protect against a short circuit is to use a molded case circuit breaker. And inside of that circuit breaker, there are two forms of circuit protection. The first looks like a coil of wire wrapped around a metal core. Sounds familiar, right? Well, next to that coil of wire, there is this thing called a trip bar. When the current passes through the breaker and through this coil of wire, it starts generating magnetism. When you get a large blast of current passing through this coil, it creates a magnet so strong that it pulls the trip bar towards it and causes the circuit breaker to trip. This is called magnetic circuit protection. Next, let's talk about a motor overload, or too much current being drawn by the motor. Well, what could cause this to happen? Let's look at an example. Here we have a conveyor belt driven by a motor. And on this conveyor belt, we have several small packages that are being moved. This motor is designed to move these small packages at a certain speed and is rated to move this load. Well, what happens if we get rid of the small boxes and instead put a jumbo package on the conveyor? Well, the motor is still going to try to move the load, but it's too heavy for the motor. The motor will try and try to move that load, but it'll be pulling more and more current as it tries to turn. Eventually, so much current will be pulled by the motor that it will overheat the inside and smoke that motor. Circuit breakers have a technology inside that prevents against overcurrent. That technology is based around two thin strips of metal bonded together. This is called bimetal. Next to the bimetal strip, there's a trip bar. Well, what happens to metal when it gets warm? It expands. And if we have two different types of metal bonded together, it's likely that one side will expand faster than the other, which will cause that strip to bend. So, as we pass current through the bimetal strip, it starts to heat up from the current. If the current becomes too great, it bends towards the trip bar until it finally trips the circuit breaker. This is called thermal protection. Okay, now let's have a little sidebar conversation about how an electric motor functions. Here I've drawn a graph of current versus time. When I start an electric motor from a dead stop, you get a big rush of current right at the beginning to get the motor up and running. After that big rush of current, it levels out and runs at about 100% speed. At 100% speed, it will pull a certain amount of continuous current until you turn the motor off. This current at full load or full speed is called full load amps, or FLA. That big spike of current you get when you start the motor is called inrush. Inrush is usually about 6 to 8 times the full load amps of the motor. Going back to the circuit breaker, we've got magnetic protection built in and thermal protection built in. Magnetic protection reacts to a very high level of current very quickly, so it is suited to protect against short circuits. Thermal protection is a slower reacting protection and correlates to the amp rating you see on the front of the circuit breaker. This is to prevent against overcurrent. But what are molded case circuit breakers designed to protect? They're hooked up to all sorts of things. You have circuit breakers feeding light circuits, outlets, motors, heaters, coffee makers, televisions, the list goes on. Well, since the circuit breaker doesn't really know what it's hooked up to, it instead focuses on protecting the wire that feeds all those devices. If it sees too much current going through those wires, it trips and allows the wire to cool down. Well, if you remember from before, when we start an electric motor, we get inrush at the beginning, causing a much larger draw of current than usual. That inrush current looks an awful lot like an overcurrent condition to a circuit breaker, since it isn't specifically designed for motor protection. Fortunately, there is a type of molded case breaker where the thermal protection has been removed, but we're still left with the magnetic protection, which still protects us against a short circuit. And that type of circuit breaker is called a motor circuit protector, or an MCP. Frequently, you'll see Eaton's version called an HMCP, with the H standing for high interrupting. So if we get rid of the overcurrent protection provided by the molded case breaker, we still need to find a way to protect the motor from an overload condition. Here we've got a contactor with our power coming in the top and out the bottom. But now let's add a new component to the contactor. This is called an overload relay. The overload relay has 3 bimetal strips inside that are designed to heat up at the same rate as the windings of the motor. This is different from the bimetals inside the breaker because those bimetals didn't know to ignore the inrush when you start the motor. When you pair an overload relay with a contactor, we call this a starter. Now that we've covered motor protection and motor control, let's put it all together. At the top of the circuit, we have our HMCP breaker, or alternately, we could use a fuse disconnect switch. Next, we have the contactor, followed by the overload relay. Lastly, we have the cables connecting the overload relay to the motor. In this setup, the HMCP provides a way to disconnect the entire circuit from power, as well as providing short circuit protection, since it still has the magnetic protection inside. The contactor provides a means of controlling the motor, and then finally, the overload relay protects our motor from overload conditions. That